we are going to continue talking about probability today. Day 3. All right, we talked about the multiplication rule a little bit the other day. It says the multiplication rule is for finding probabilities such as probability of A and B, which means the probability that events A occurs and event B occurs. The key word to note here is and, meaning both occur. When the events are independent, and two events are independent events if the occurrence of either of them has no effect on the probability of the other, then you have probability of A and B equals the probability of A times the probability of B. If you have dependent events, it's the same formula, but your denominator of the second event is going to be changed because if one is dependent on the other, which you'll see here in a second. All right, so it says decide if the events are independent or dependent. It says Andrew lives in Texas and the probability that he will be alive in 10 years is 0.72. Ellen lives in New York and the probability that she'll be alive in 10 years is 0.92. Do we have any reason to believe that the lifespan of one of these people will affect the lifespan of the other? Absolutely not. Oops. Yeah. No. Ain't gonna happen. Why? Because this guy in Texas will probably never even look at her. They have nothing to do with each other. Nothing's the same. Environment, nothing. So this makes them independent. So it says, then find the probability that both Andrew and Ellen will be alive in 10 years. So I'm doing probability of Andrew and Ellen. And all I do is take the probability of Andrew, which he has a 0.72 chance of living in 10 years, being alive in 10 years, times the probability of Ellen, who has a 0.92 chance of being alive in 10 years. And you multiply those together. And here's a way that you can, instead of writing out the word and, you use the upside down, where you use for or, it's union, for and, it's intersection, and they use that one. And so I multiply those out and I get 0.6626. Okay. All right, so in example 2, it says a bag contains 18 suckers. 7 are cherry, 5 are orange, 6 are grape. Sheldon and Aaron are drawing suckers randomly from the bag. Sheldon randomly picks a grape sucker and eats it. Then Aaron randomly picks a cherry one. Will Sheldon's choice have an effect on the probability of Aaron getting a cherry sucker? Yes. Why? Because now, once Sheldon picked one and ate one, Aaron only has 17 to choose from. He doesn't get the same choice that Aaron did because one of the suckers is already gone. So to find the probability of Sheldon picking grape, I'll put S there for the probability of Sheldon picking grape, then Andrew picking cherry. Well, the probability of, I can't keep the people straight now, Sheldon picking grape, there are 6 grape suckers out of 18. So that's the chances of Sheldon pulling a grape one. But now when Aaron draws a sucker out, there's still 7 cherries in there, but there's not 18 suckers in there anymore. Oops, we're not doing plus for many times. Now there's only 17 suckers in there. So now I multiply those and I get 42 over 306. Math enter it. And you get, I guess I just left it as a decimal, 0.1373. All right, so you try one, hit pause, come back when you're ready. And these events are independent. You flip a coin and get tails. You flip it a second time and get heads. Getting tails on the first one has no effect on what it's going to come up on the second time. Just because you flip heads once doesn't mean you'll flip it twice, or if you flip it once, it has to do the other one next. They are independent. Okay, do this one, hit pause, come back when you're ready. You spin a spinner divided into 5 equal parts and is numbered 1 to 5. You get a 3 on the first spin and then spin again and get a 2 on the second spin. whatever you spin the first time will have no effect on what you get the second time. So again, these are independent. Hit pause, come back when you're ready. You remove a black sock from a drawer without looking, then remove another black sock. These are dependent because once you remove a sock from the drawer, then your options to get your second sock are going to be different. So one is dependent on the other. And one more. Hit pause, come back when you're ready. You pull your friend's name out of a hat that holds 20 different names. You put it back and then draw out your friend's name again. Those are independent. If you wouldn't have put it back and then tried to draw another name, then they would be dependent, because then you would be changing how many choices, how many names are in the hat. But if you put it back before you draw again, that keeps them independent. Okay? Alright, so this one says, remember our little picture of our squares and triangles and circles? It says you randomly choose two shapes, but you replace the first one before you choose the second one. So the probability, first, if I get my little totals here, there's 7 triangles, 4 are black, 3 are white. There's 10 circles, 5 are black, 5 are white. There are 3 squares, 3 are black, none are white. Okay? So it says find the probability that you do a triangle first and then a square. Well, triangle, just picking a triangle, not specifying white or black, I have 7 chances out of, there's a total of 20 objects there, 20. These are independent because what you pick, you put it back before you pick the second one. So whatever you pick first, because you're putting it back, has no effect on what you pick the second time. So the probability of getting a square, there's 3 squares out of 20. So to find that product, you would get 21 out of 400. So the probability of choosing a circle and then a triangle. Well, a circle is 10 out of 20. A triangle is 7 out of 20, which gives me 70 over 400, which reduces down to 7 over 40. 3. The probability you pick a black triangle and then a white circle. Well, there's 4 black triangles out of 20 things, and there are 5 white circles out of 20 things. That gives me 20 over 400, which gives me 120. The probability of a square then a square? Well, the square is 3 out of 20. Because you put it back, when you draw again, there's still 3 to choose from, and that would give me 9 out of 400. Done. Alright, so now we're going to talk about dependent events, because now you are not going to replace the first one before choosing the second. So now we're talking about dependent, which is going to affect the denominator of our second choice. So the probability of choosing a triangle. There was 7 triangles out of 20 objects. But since I don't put it back, now when I draw my next one, there's not 20 objects anymore, there's only 19. And 3 of those are squares, and that would give me 21 out of 380. Okay, so the probability of finding a circle and then a triangle. Well, my circle, there are 10 circles out of 20 objects. But if I pull one out, when I go to make my second draw, there's only going to be 19 things left. And how many of those things are triangles? 7 of them, which gives me 70 over 380, which reduces down to 7 over 38. 3 says, find the probability of choosing a black triangle and then a white circle. Well, there are, I don't remember, 4 black circles out of 20. But now when I make my second draw, there's only going to be 19 objects in there. And 5 of those are white circles, which gives me 20 over 380, which reduces down to 119. Okay, so then it says find the probability of square and then a square. Well, there are 3 squares out of 20 objects, but if I draw one, if I draw a square, and I don't put it back, that's going to make my denominator 19. But if I draw a square, that also means there's not 3 squares left to choose from. There would only be 2. So be careful. Both of these had to change. And that gives me 6 over 380, which reduces down to 3 over 190. Okay? Alright, so some other helpful hints when working with the multiplication rule. It is common practice to treat events as blank when small samples are drawn from a large population. We are going to treat them as independent. Okay? You're talking about like if you're looking at a population of, I don't know, 300 people compared to the United States. Okay? That sample is such a small sample of the larger population that we would consider them independent even though they really wouldn't be. So the general guideline is if your sample size is less than or equal to 10% of the population, we treat them as independent, even if selections are made without replacement. Now, the other thing is you're going to have this finding at least 1. To find the probability of at least 1, find the complement of the probability of getting 1. So the rule for that would be probability of at least 1 is 1 minus the probability of none. Okay? That's just a helpful hint. Okay, so it says you roll 2 fair dice. I don't know why those are away. You roll 2 fair dice, 1 green and 1 red. Are the outcomes on the dice independent? Well, yes. Whatever the first dice, the number on first won't or doesn't affect whatever number shows up on the second. Okay, so yes, they're independent. It says find P of 5 on the green die and 3 on the red die. Well, there's 1 5 out of 6 numbers that's on the green die, and there's 1 3 out of 6 on the red die. So the probability of both is going to be 1 over 36. Okay, find P of 1 on the green die. Well, again, there's only 1. And 4 on the red die. So that would be 4 out of 6, which no, I'm sorry, 1 out of 36. 6. Eek. Again, 1 out of 36. Okay, so it says, what is the probability of 5 on the green, 3 on the red, or 1 on the green and 4 on the red? Well, 5 on the green is 1/6, 3 on the red is 1/6, that's 1/36. 4 means plus, 1 on the green means 1 out of 6, 4 on the red is 1 out of 6, and that gives me 1 out of 36. And now if I add those, I get 2 out of 36, which reduces down to 1 out of 18. Okay. Alright, so now let's look at cards. You select 2 cards at random from a standard deck of 52 playing cards without replacing the first one, which means we're talking about dependent events. So watch your denominators. So the probability of 2 hearts, what they're asking you to find is the probability of the first card being a heart and the second card being a heart. Well, the probability of the first card being a heart, there's 13 hearts out of 52 cards. If you don't put it back, when you make your second choice, there's only 51 cards left. And when you do doubles, if I already got ahead, then the chances of getting the second one, now there's only 12 left that I could possibly pick. So we have 13 over 52 times 12 over 51, which gives me 156 over 2652, which reduces down to 1/17. You could also write your answers in decimal form. I'm not really sure what, oh, you're not doing Math Excel. I don't care which way you write them. All right, a probability that you draw a face card and then a 2. Well, a face card is, there's 12 of them, because you got a Jack, Queen, King for each of the 4 suits. So there's 12 face cards out of 52. Then a 2. Well, the only thing that's going to change here is since you don't put it back, now there's only going to be 51 cards in the deck. and these don't overlap. So how many of them, how many twos are in a deck? There's 4. There's a 2 of hearts, 2 of clubs, 2 of spades, 2 of diamonds. So if I multiply those, I get 48 over 2652, which reduces down to 4 over 221. C, the probability of a club and then a spade. There are 13 clubs out of 52 cards. The second draw, there's only going to be 51 cards. And there are 13 spades in the deck. So if I multiply those, I get 169 over 2652, which reduces down to 13 over 204. So for D, probability of a face card and then a face card, well, there's again 12 face cards out of 52. When you draw your second draw, there's only 51 cards left, and if you've already drawn a face card, there's only 11 of those left. So we multiply that, we get 132 over 2652, which is 11 over 221. Alright, for E, probability of 3 and then a 10. There are 4 threes out of 52 cards. There are 4 tens out of now 51 cards. That would give me 16 over 2652, which reduces down to 4 over 663. And are these incomes independent? No, because second choice has different total. Okay. Alright, so a little bit more here. You select 2 cards at random from a standard deck of 52 playing cards, but before you draw the second card, you put the first one back. So now we have independent events. So it says find the probabilities as simplified fractions. So probability of 2 clubs. So they're asking you for probability of a club and then a club. Well, the probability of getting a club, there's 13 out of 52. Since you put the card back, there's still going to be 52, and there's still going to be possible 13 to choose from. So that gives me 169 over 2704, which is 1 over 16. Probability of face card, then a 9. Face cards, there's 12 face cards out of 52. There are 4 nines out of 52. Again, it stays 52 because even if you draw a face card, you put it back before you draw your second one. So that gives me 48 over 2704, which reduces down to 3 over 169. Probability of a club and then a spade. There are 12 clubs out of 52 cards, and there are 12 spades out of 52 cards, which gives me 144 over, oh my gosh, sorry, there's 13 clubs and 13 spades. That's 169 over 2704, which reduces down to 116. Okay, probability of a black card. Well, all your clubs and all your spades are black. That's 26, half the deck out of 52 is black. Then a heart. So whatever you draw, you put back. There are 13 hearts out of the 52 cards. And that gives me 338 over 2704, which reduces down to 1/8. The probability of a 7 and then a queen. There are 4 sevens in a deck. There are 4 queens in a deck. Right? And you put them back so the denominators are the same. That gives me 16 over 2704, which reduces down to 1 over 169. And yes, they're independent because you replaced it, so it doesn't change your chances of your second draw. Okay? Alright, it says the Master Foods Company manufactures bags of peanut butter M&Ms. They report that they make 10% each of brown and red candy. So I'm going to make me a little chart here. We've got brown, we've got red, we've got yellow, we've got blue, we've got orange. And it says that they report that they make 10% each of the brown and red. So that's 0.10 and 0.10. 20% each of the yellow. So that's 0.20, 0.20, 0.20. Oh, and the rest of them are green. Well, how many is left? 10 and 10 is 20, and 20 is 40, and 20 is 60, and 20 is 80. That means there's also 20% green. But he was trying to trick you. Instead of just saying them all, he was going to see if you were going to miss that. All right, now we are going to treat these as independent. Because if you're talking about bags of peanut butter M&Ms, all right, and we're picking two out of an entire bag, we are choosing less than 10% of the total population of M&Ms. So we are going to treat everything as independent. So we have probability that both are green. So they want probability of green and then green. Well, my probability of green is 0.20. My probability of green is 0.20, which gives me 0.04. They want that neither of them are orange. So they want not orange and not orange, if you wrote it in that one. Okay, well, you have a couple ways of doing this. Okay, if you're trying to do not, then you could do the 1 minus 20, right, which would be 80. Or you can say you win if it's not orange, which would be here, 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 and here. Well, again, if you add those up, 20, 40, 60, 70, 80. So the chances of it not being orange are 0.8. And the second one not being orange is 0.8, which gives me 0.64. Okay, probability of red then brown. Red is 10%. Brown is, where's brown? 10%, which gives me 0.01. All right, so to find the probability that at least one is blue, at least one blue, I'm going to basically do the complement, which is going to be 1 minus the probability that it's not blue and not blue. Okay, so I have 1 minus the probability that it's not blue would be everything but the 20, so that's going to be 0.8. And not blue would be 0.8 again. So that would be 1 minus 0.64, which would be 0.36. Yeah. Alright, and now you're picking 4 peanut butter M&Ms. 4 peanut butter M&Ms in a row randomly. And let me get my brown, red, yellow, blue, orange, green, 0.10, 0.10, 0.20, 0.20, 0.20, 0.20. Alright, so probability they're all blue. So you're trying to find probability of blue, then blue, then blue, then blue. Well, the probability of blue is 0.2. Probability of blue is 0.2. Probability of 2 is, we're treating them as independent because, again, we're looking at 4 of the whole bag. That's less than 10%. So that would be 0.001. At least 1 is red. That means 1 minus the probability that it's not red. So I have 1 minus, if the probability of it being red is 10%, then the probability of it not being red is 90%, which, oh, no. Oh, that none are red. My bad. 1 minus the probability that it's, oh, none are red. Okay, yeah, but, I'm sorry. So we're finding, yeah, I like doing it this way. We're finding the probability that it's not red, not red, not red, not red. I think it's easier than doing that. So if it's not red, that would be 0.9. Not red, 0.9. Not red, 0.9. Not red, 0.9. So the probability that all of them are not red is 0.9 to the 4th, which I'm going to have, yeah, you're going to have to do this. Okay, so here's the probability that none of them are red, because we to do at least one, we have to do 1 minus the probability that none are red. Well, that's 1 minus 0.9 to the 4th, because that's what the probability of not red is. And that gives me 1 minus 0.6561, which gives me 0.3439. That's my probability that at least one is red. Okay, the probability that none are green. So the probability that not green, not green, not green, not green. Well, if the probability of green is 20%, then the probability of not green is 80%. So 0.8 times 0.8 times 0.8 times 0.8 gives me 0.4096. D, the fourth one is the first one that's brown. So they want the first one not brown, the second one not brown, the third one not brown, but they want the fourth one to be brown. And the fifth one, I don't care. It doesn't matter. I'm just interested in the fourth one being the first brown. So probability of the not brown would be 0.9, not brown 0.9, not brown 0.9, brown 0.10. So then when I multiply all those out, I get 0.0729. All right. So it says, after picking 10 peanut butter M&Ms in a row, you still have not picked a red one. A friend says that you should have a better chance of getting a red one on your next pick since you have yet to see one. Comment on your friend's statement. Well, he's wrong, because the probability of picking a red M&M is always 0.1, because if you're picking from a large bag of M&Ms, we assume independence even if picking items without replacement. All right. So it says 5 multiple choice questions, each with 4 possible answers, appear on your history exam. What is the probability that if you just guess, you get none of the questions correct? Well, to get a question, if each question has 4 multiple choice answers, okay, so you have A, B, C, D to choose from, yes. The probability, okay, for each question, 1 answer is correct and 3 answers are wrong. So your probability of getting it correct, each question correct, to get 1 correct out of 4, you got a 25% chance. To get 3 out of 4 wrong, that's going to be a 70. So you have a 25% chance of getting it right and a 75% chance of getting it wrong, each question that you answer. So A says none of the questions correct. So they want the probability that you get 1, 2, 3, 4, 5 questions wrong. Well, the probability of getting a question wrong is 0.75 times 0.75 times 0.75 times 0.75 times 0.75, which gives you 0.2373. Okay, so about a 23% chance, 24% chance that you'll get them all wrong. What about getting them all correct? The probability that you get 1, 2, 3, 4, 5 questions right. Well, the probability for getting it correct is 0.25 times 0.25 times. And if anybody's sick of writing this out, you have figured out I could just do 0.225 to the 1, 2, 3, 4, 5, right? But I'll write it out. 1, 2, 3, 0.25, 0.25, and I get 0.00098. And that means, guys, you don't even have a 1% chance of getting them all right. Crazy. All right, C, it says get at least 1 of the questions wrong. Well, that's going to be 1 minus the probability of getting none wrong. Yeah? Well, didn't we already figure out if you're looking for the probability of getting none wrong, that means it's the same as the probability of getting them all right. So wouldn't I just have to take 1 minus whatever I got right up here, 0.00098, and that would equal 0.9990. Yeah? You got a 99% chance of getting at least one question wrong. D says, get your first incorrect answer on the fourth question. So again, they want, get the first what? Incorrect. So correct, incorrect, wrong, and then it does, I don't care about the fifth one. So this would be 0.25 times 0.25 times 0.25 times 0.75, which is 0.0117. All right, hit pause, come back when you're ready. All right, it says an automotive manufacturer buys computer chips from a supplier. The supplier sends a shipment containing 5% defective chips. So each chip chosen from this shipment has a probability of 0.05 of being defective. If each automobile uses 12 chips selected independently, what is the probability that all 12 chips in the car work properly? You're trying to find the probability that, what are we talking? Chips? So we want to know all, what's the probability that all chips will work properly? I don't want to use the word E. How about we use the word P for works. All right, so the probability that 12 of them work. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, if there's a 5% chance that it's not going to work properly, then there's a 95% chance that it will. There's a 5% chance it'll be defective, which means there's a 95% chance it'll work. So each of these is 0.95. And I do not want to type that in. You get that that's going to be 0.95 to the 12, which is 0.54036000877, and it wants me to round 4 places out, negative 5404. Okay, try this one, hit pause, come back when you're ready. Alright, a teacher asks each student in the class to randomly choose numbers from 1 to 50 and write it down. Jerome and Denise each write down a number. Find the probability that both students' choices will be greater than 35. Express your answer as a decimal round to the nearest tenth of 1,000. Alright, 1, 2, 3, 4, I'm not counting all the way to 50. But we're knowing that around 35. So if I go 34, 35, 36, dot, 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 dot. And then we're going up to 50, so 48, 49, 50. All right, basically, find the probability both shows be greater than 35. So 35 is my, greater than 35 would be here up, because it doesn't say we're equal to, so this would be less. Well, on this side, so the probability of getting less than 35 would be, you've got 35 chances out of 50. Yes? And these would all be wins. And there would be, how many of those? 15 numbers up here. So the probability of winning, or getting a number bigger than 35, would be 15. So the probability that both, and they're independent because you're writing it down. It's not like if somebody picks your number, you can't use it. You have no way of knowing. So they're independent. So the probability that both answers are above 35 would be 15 out of 50 times 15 out of 50, which is 225 over 2500, which is 0.09, which is 9/100, which they gave it as a decimal. Alright, so we are at homework, Happy homeworking, and I will see you next time.